Good evening, ladies and gentlemen. Welcome to Reference Point. I'm your host, Dave Cokerhook. And this evening, I'm actually very much looking forward to this evening's conversation with a good friend and colleague, Jordan Makower. Jordan, welcome to Reference Point.
Thank you.
And Jordan has a pretty complete resume, let's just say. I mean, he's an author, he's an educator, he's a researcher, he's an instructor, he has information in, I don't know if it's degrees in all of them, but in geology, astronomy, chemistry, just like it goes, meteorology, it goes on and on. So he's done a tremendous amount of learning, and so and he and I get a chance to get together periodically. And one of the reasons I asked him to come and join us today is so that we can talk about something that we're all starting to see in the news very regularly, but I think we don't have a good understanding about, and that is what's going on in the cosmos up there. We get these cool pictures from, we've been getting them from Hubble for a while, but now we got these incredible pictures from James Webb, and it changes the impression that people have of what's going on out there in the cosmos. Is that a fair statement, Jordan?
Yeah, it is. The James Webb Telescope has 100 times the light gathering capacity, the energy gathering capacity that Hubble has.
100 times.
Yeah.
So we can get a lot more clarity and see further.
Yes, and an advantage of the James Webb Telescope is that it gets its images in the infrared, so it can see through the dust that would normally obscure viewing and light. And of course, it's a million miles away from the Earth, parked in one of those special orbits that allow it to see unimpeded by the Earth's atmosphere.
So when you say it can see through the dust, you're talking about cosmic dust, dust that's out there, not dust that you have to look through from, you know, anything that's around Earth, right?
Well, it gives you an example. To give you an example, everybody must have seen a sunset where the sun appears reddish, but you know that when the sun is higher in the sky, it's yellow.
Right.
So the reason why it appears reddish is because you're looking through the dust in the atmosphere, and that reddening happens in space as well, because there's dust in space as well. So that can give you all sorts of misleading information and prevent you from getting information.
Right. So something that you and I had talked about, and I remember seeing in some images that were online, was that when they first look at the image that they capture from the James Webb, it's in black and white. And then because of the information that they're able to capture from the other data that they've accumulated, they're able to colorize the photos after the fact. Am I saying that right?
Pretty much. The data comes in, of course, everything comes in electronically.
Right.
So there's some conversion between the Webb scope picking up information in the infrared and then transmitting it. It transmits electronically to Earth, where that infrared is then changed. It's changed in frequencies to bring it into the visible, because we can't pick up infrared with our eyes.
Can't pick up infrared.
We have a very narrow range of color that we can pick up. Infrared we can't see. We can feel the heat, which is infrared.
Right.
We can you can get a sunburn from the ultraviolet from the sun, but again, you can't see that.
You can't see that, right.
So
I've got a graphic. It's graphic number 14. It's this one. It talks about the electromagnetic spectrum. And the thing that's interesting on it is that it shows how narrow the actual visible light range is, which is just like amazing. All this other electromagnetic waves are various and sundry other forms of energy that we don't see. But my understanding is also that there are certain animals on the planet that can see in some of these spectrums that we can't see.
Unfortunately,
But we'll go into that. That's a whole other conversation. We don't want to go there.
biology is not my
Yeah.
my forte.
Right. So, yeah, but I thought that was really very interesting that it is that limited. Okay, so one of the things I really wanted to talk about today, and this is because I think that we here, as we walk around the planet, tend to think that we're the big fish in the pond, right? And when actually this pond is pretty immense, and in trying to understand orders of magnitude and relative size of things, I think is useful, because this is not something that I've ever done when I was in school. We're going to talk about here. It has to do with getting a sense of how big the sun is relative to the Earth and some of the other planets. Because when you look at something online or in a textbook, it's like, oh, here's the sun, and here's the little planets, and they make them big enough so you can discern what they are. But these differences are pretty profound and huge. Yeah?
Yeah, to get into this, there's an ancient, I'll call it a proverb or a teaching saying, I hear, but I forget. I see, and I understand. I do, and I really understand.
Right. Yeah. So I wanted to give us here, and everybody that's watching the show and the team here in the studio, some sense of order of magnitude just in our solar system. And then we'll go to the universe. I got some other graphic for that. But when we look at the solar system, we've got the sun, and then we've got the planets up through, well, I guess Pluto's not considered a planet anymore, poor Pluto. But you brought some stuff that gives us some sort of a sense of perspective. Now, we're not going to be able to figure relative distance, but relative size is what I'm looking at right now. So what we did is we got this, I'm going to kind of move and stand up here. We got this thing, and this is a beach ball that's about 42 inches in diameter, right? So if this is the sun in our solar system,
why don't you plant that down over here?
I'll plant that down there.
Okay.
What does the Earth look like size-wise?
Okay. First, to talk about the illustration you see on a textbook.
Right.
Their job is to show you everything, and so they're using two different scales. They're using one scale for three different scales. One scale for planetary distance, a different scale for planetary size, and the sun.
It just blows it all out of the water.
Correct.
It does. It's just, yeah.
So if this is the sun, which is approximately 864,000 miles in diameter, pretend that this is
864,000 miles in diameter. Then I'm a pretty big guy.
Keeping the same scale as that.
As this, right?
If you could take a pace, a walking pace, which is slightly bigger than a normal step. If you could take 80 of those paces,
and that
you would
the
eventually
approximate distance that
would take you to the planet Mercury.
The planet Mercury, okay.
And here, this little BB.
I don't know if we can see. I'm going to have you put that. I don't know if we can see this. This is super tiny. But what we have here is a ball bearing. It's the size of a BB. I don't know if you. I'm going to put it on the desk here. I don't know if you guys can manage to see what that is. This is like super tiny.
You could put it here, slightly recessed.
And it is just like so. So that would be the relative size of Mercury to the sun. I mean, that's like just tiny.
80 strides away.
Yeah. Long ways.
One.
I get that.
2.
And then Earth.
Okay.
Earth is a little bigger than Mercury.
Earth is approximately 200 paces away.
And what's its size relative to Mercury?
Okay, so Mercury is approximately 3,000 miles in diameter, and the Earth is approximately 7,926 miles in diameter through the equator.
Okay, all right. So it's multiple times bigger. But that then, compared to this thing, how many Earths could fit in the sun?
You could get 100 Earths side by side in the sun and 1,000,000 Earths to fill it up.
1,000,000 Earths to fill up the volume.
Right.
Okay. All right. So that tries to give us a little sense of this order of magnitude, because it's like immense. The whole thing about what's going on that we're observing from the what we see on Hubble, what we saw on Hubble, and what we're seeing on James Webb, gets this sense of, boy, there's a lot going on out there. Okay, and one of the other things that so we look at the size of our sun, and it looks pretty darn big relative to Earth, but it's actually not one of the bigger stars, is it?
No, we could say it's an average star, and one of the graphics I sent you, the one that I can see right now,
yeah, it's
in the lower right.
It's number 2, graphic number 2.
Right, shows the Earth as a little white dot in the upper left of the screen, and then it shows a huge red ball,
right,
which is a star Betelgeuse,
right, that's right,
which is thousands of
Orion,
times,
right?
correct,
Yeah.
one of the bright stars in Orion, thousands of stars, thousands of sizes bigger than the Earth, and so there are all sorts of other stars.
Yeah, but and so when we think about what we've got here, our star, I mean, it's cool. It does its right things for us and all that kind of good stuff. But relative to the size of some of these other things out in the universe, it's not that huge.
Yeah.
Okay. Another thing that is amazing to me, one of the things that has come up, and I've been reading about this now for the last, I don't know, as far as serious consideration, for probably the last 7 to 10 years. And there's been all kinds of science fiction movies and things like that about harvesting metals and other things from asteroids and other kinds of planetary bodies, et cetera, so that because of... Well, what's interesting to me about that is what it's telling me is that kind of material is not an earthbound material. It doesn't originate on the planet. It's out there in other heavenly bodies. So that means it's coming from somewhere else. Where does all this stuff come from?
Once upon a time, a long, long time ago, there was a cloud of dust and gas, which I can illustrate.
Give me we got to.
Okay.
Yeah, we're running.
Okay.
We're running along.
So, cloud of dust and gas, and gravitationally, this dust and gas was drawn together, and most of it, 99.8% of it, formed our sun. However, the other small percentage formed all of the planets.
So 99.8% of the mass in our solar system is in the sun.
Correct.
99 point, so that means 0.2% is the planets and the asteroids and all
the
that.
Meteors,
the meteors and all
the
that
comets.
Kind of stuff. That's not a lot.
No.
But what was interesting to me, something you had mentioned at a discussion we had a couple weeks ago, was how these other materials are made. Oh, I understand, and I think a lot of people know the sun operates as a fusion reactor, and hydrogen atoms.
4 hydrogens make 1 helium.
And there's something. But you were telling me that as a stellar body evolves, it emits these other elements through some sort of compression and explosive kind of a thing. Could you go ahead?
Okay, generally, if you have, first of all, Carl Sagan said a long time ago that we are made of star stuff.
Mm-hmm.
All the elements that we are in contact with, the elements that compose us, the elements that compose the Earth, the planets, the asteroids and meteors and the comets, all of that was forged by this stellar action, and we are the third rendition of that type of formative process.
In our solar system.
In our solar system.
Third iteration in our solar system.
Correct. So when the huge, massive object was here before, and it compressed and formed hydrogen and helium, and as it did that, it began to fuse helium and hydrogen into other elements. So all the elements were built up, especially during the supernova type explosion that would happen at the end phase, near the end phase of the life of those supermassive stars.
So does that mean that one of that maybe the first iteration of the star in this solar system was much larger than the one we have today?
Certainly the previous iterations were larger. And we scavenged up the remains to make our sun and the planets that we have today.
Got it.
Previously, when those other stars were here, they gobbled up whatever planets might have been here.
Might have been in that
and
area.
just absorbed them
right in.
and reworked them. And
then here we are today.
We are the product of those iterations.
That process is a process that's understood and known by astronomers and, I guess, geologists and science in general, yeah?
Astrochemicists.
Astrochemicists. So that means that this has been going on in all parts of the universe for however many billion newtons of years that they say that the universe has been here.
13.8 billion years.
13.8 billion years. Okay. And we're seeing, see, that creates another interesting thing, because they're saying that using the James Webb, we're able to capture light images of activity that was, many billions of years ago. So this was like a lot of stuff has happened since that light got to us. So that means that this is a pretty huge space, this universe thing. It's kind of like massive, size-wise. And there is this, I got another graphic here I want them to pull up, and I'll tell you which one it is, guys. It's number 13. You probably saw this one. I think I sent this one to you. This is this graphic that talks about how they are able to discern that the universe is continuing to expand, but its rate of expansion has increased. Now, how do they figure that out?
Okay. I can't give you a one-sentence answer for that.
Well, that's okay.
It's going to have to be a little bit larger.
A couple of paragraphs.
The way they got started on this was even prior to the 1960s, when Wilson and Penzias were working for Bell Laboratories at Holmdel, New Jersey.
Okay.
And they had built this gigantic device to help with satellite communication back then, and there was this constant hiss that they were picking up. And they were assigned to try to figure out, I got to stop that hiss. And they determined that it was coming from all around us. They were picking up the remnant heat from this huge formation of our universe, some 13.8 billion years ago. So here's how we know about the distances and the time. Through the use of a spectroscope. Spectroscope is a device that will, like a prism, break light up into colors red, orange, yellow, green, blue, indigo, and violet. And in addition to that, will show lines, whether they're dark lines or bright lines, to indicate patterns that represent elements.
Okay.
And if these patterns are shifted to the red, and most all of them are shifted to the red, it means that object is moving away from us.
Okay.
It turns out that all the galaxies, almost all the galaxies, are moving away from each other as,
that's interesting.
as the area that they occupy becomes greater and greater and greater.
Okay.
Now, if you could get measurements over thousands of years rather than just the 20, 30, 40 years since Hubble has come out, people have noticed that the rate of expansion, I don't want to say that, the rate of movement may be slowing down.
Ah,
Okay, and if that is the case, then there are several things that are happening. One is the galaxies are moving into areas that they haven't been in before. Two, the galaxies are moving away from each other.
right.
Three, the rate of that change may be slowing down. But in order to really know that it is, more images, more data has to be collected.
And this is where Hubble and other research activities that are being done by both the U.S. and the EU and other places are trying to pull this information together.
Correct.
One of the things about this that I think is relevant and important, we tend to hear on our everyday lives here on Earth, we get all caught up in the most interesting and bizarre, and in my opinion, nonsensical things that create, conflict and tension amongst people and stuff like that. If you spend some time out where it's not like lights of the city, and you just gaze up at the night sky. I had the opportunity to do this when my wife and I went to South America to go hike up to Machu Picchu. We're up there at 14,000 foot elevation in the middle of nowhere. There wasn't any, the only light was your flashlight if you turned it on. And looking at the night sky, it's just like you really get a sense of awe, okay? And that, to me, generates perspective. And there's so much that we can learn and do. And I think the other thing, I'm babbling, but one other thing that comes to mind here is there are sources of energy that we are able to discern through the research from some of the other masses out there. It's certainly fusion, and then there's some of these other, I don't know if it's different in things like pulsars or some of these others, it's the same type of energy creation. But it's just so interesting to me that there are opportunities that we need to explore and take advantage of.
Interesting. When you were at Machu Picchu and you looked at the sky, every single object that you saw was in our galaxy. And 100 years ago, in 1920, a scientist named Shapley believed that that was it, that was our universe. And then as instruments began to develop with the power to see deeper, and people would analyze the light given off by stars and galaxies more distantly, they determined that there were galaxies, many, many galaxies, and the thing I'd like to cling to is in December when the James Webb Space Telescope was launched. The introduction was the gentleman giving the lecture said, "Here's a grain of sand. If I hold that at arm's length, this is occupying all of the galaxies that I can show you in this picture." And there are billions of galaxies. And the picture, of course, only showed that much space for all the galaxies that would fit in the image that they showed. The universe is huge.
It's huge, yes. We have like 4 minutes left in the show, but I'm going to ask if you would be willing to stick around for a little bit, and maybe we can do another quick segment here, because there's some other things I want to talk about relative to how they're able to capture some of these images, because it's a little different than some people might understand. And the other thing that we'll like to talk about in the next segment is how do we ascertain this stuff that is referred to as dark matter and dark energy and all that kind of stuff. So there are some other things, astronomical things, I'd love to talk about. But we're running short of time. We only have a couple of minutes left. One last thing, I think, before we're able to, Hubble is an optical telescope, excuse me, James Webb is an optical telescope, right?
Well, if you, it isn't a human optical telescope.
Right.
It's because it gets in the infrared, several different regions in the infrared.
Right.
So when you say optical, then you're implying visible light.
Right.
And
okay.
when we talk about the universe, we're talking about the visible universe,
Right.
which is only 5% of the matter that we perceive. There's 95% of dark matter and dark energy
Yeah, which
that's out there.
which we'll get to in a minute, but in the next episode. But then, relative to the type of, I think we got about 2 minutes left here. But I just want to ask one other thing about types of telescope, because there's a kind that I had when I was a kid where you put it up and you say, oh, look, I can see the moon. Isn't that cool, right? And then these, like James Webb, is now able to capture light from a variety of spectrums. But there are radio telescopes too. What is a radio telescope?
Okay, a radio telescope is a huge antenna that captures energy from space, radio energy of 30 megahertz to 100 megahertz, and focuses that energy onto a little box that decodes the signal, sends it to a computer, and the computer then will generate an image of what is being scanned.
It can generate an image based on the wavelength that it's picking up.
Correct.
Ah, okay, see, I didn't understand
So
that.
it transfers the electrical energy that it's getting into a visual image for us.
There you go. Folks, we're going to leave you with that thought. We'll be back for another conversation with Jordan Makower here in a little bit. Just as a reminder, if you have any questions about anything associated with this, send them to info@referencepointtv.com. I'll get them to Jordan. Jordan does lectures here and around the Bay Area as well, on a variety of topics, including astronomy. I was at a little talk he gave a couple of weeks ago. So, Jordan, thank you for being here. Appreciate you're going to stick around for another conversation. We're going to get into some of this stuff on dark matter and blah, blah, blah. But right now, folks, stick around. We'll see you next time.